Can we go
like all over, like the top was
on
just
which one?
Which one? What'd you say?
Number 8.
Oh, I thought you said can we go over the weight? That's what I thought you were talking about.
No, we were talking.
Okay.
Yes.
Now, on number 8, here's the setup. So, here's Bubba in a barrel.
I don't know what I did.
Did the tension.
I was writing tension.
And literally, on the test, I will tell you, Bubba is in a barrel. Okay? Bubba is going to be in a barrel spinning around like this. So the first thing you have to figure out are the 3 forces acting on Bubba. What's one of them?
Gravity.
Gravity. The floor has dropped out, gravity is acting down. That's one of them. What's the second one?
Friction.
Friction, which is going to be acting upward, which is going to oppose that gravitational force. And the third one, the centripetal force acting inward at right angles to the surface. So here's the deal.
That will do something.
So when you look at it, kind of draw that a little bit. Where it's, okay, you get the idea.
What is that?
So here's the deal. When you look at mu equaling force friction over force normal, right? What is the, if he's going to stay there, what does the frictional force have to balance out? Gravity. Okay? So this is going to be mg. The normal force is mass times your centripetal acceleration. Okay? So you can go like this. I gave you mu, you know g. You can figure out what the centripetal acceleration is. Okay? Boom. Now, once you get your centripetal acceleration, now you can spin it one of 2 ways. You can either go v squared over r, or you can go 4 pi squared r over t squared. So you've got mu, you know what g is, find your centripetal acceleration. Then from there, I'd go with the 4 pi squared r over t squared, and then do that. Now, but here's what you have to be careful of. Let me see if is that you're told that it spins at a half a revolution per second. Is a half revolution per second frequency or period?
Frequency.
That's frequency. And if you take the inverse of that, you get period. Okay, so you know everything but the radius. Your radius should be somewhere between 5 and 10 meters. Everybody cool with that one? 5 and 10.
Wouldn't that depend on what your time is?
That's not what mine is. 1.11.
It would, and that's why I tell you that it's making a half a revolution per second.
7.
You said at most.
Did you get
Okay.
8 right?
I
That's,
thought you were saying we could design it out.
Yeah, can we see?
no, you're just trying to find the radius that matches that.
I need to figure out
In other words, it can't go any faster than that. That's what it's going to be spinning at. Okay. Your answer to number 5 should be around your age-ish. Okay?
Give or take.
It's an ish. Okay? It's an ish.
What about number 2?
Your answer to number 2 should be a pretty big number, like something times 10 to the third.
All right. To the third. Yep. Wait.
Now, technically your answer to number 3 is a negative number, but here's the deal on number 3. Because of the fact that you're going over the top of the hill, okay, like this, right? You're going up like this. You couldn't make you couldn't take your car and drive it like on an inside loop of the track, but you can go over the top of the track. So because the track basically then is going to be making up the difference between the centripetal force that is going to need it to keep it moving in a circle and the gravitational pull. So as long as, if you're on an outside, that's cool. It's a negative number. All that tells you is that that would be the reading on the scale if you could put scales underneath the car at that point. So that's all that means. So when you get to part B on number 1, okay, do not just tell me yes or no. You have to justify why. And there's three things that you can look at. You can look at the relationship between the centripetal force and the gravitational force. See which one's bigger. You can look at your centripetal acceleration versus your gravitational acceleration. As long as your centripetal acceleration is bigger, you'll make it. Or you can use that v equals the square root of GER, which tells you the minimum velocity that it needs to complete the loop. So if you find the minimum velocity and you're going faster than that, then you're okay. So there's three different ways you can answer 1b. I don't care how you answer it, okay? Just don't tell me, oh, yes. And the worst thing that you can say is, oh, yes, it will because the force is positive. I thought, which force? Centripetal force, net force, gravitational pull, well, I don't know what that is. So here's what I do not want as an answer on B. The force is positive. Way, 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 way too nebulous.
Is it okay if we say yes because when there's just something that's larger than the required velocity?
Lovely.
If I draw an arrow to my left.
No, arrows are bad. Arrows are bad. What do I say? Explain, not draw an arrow.
I have all the words there.
Yes, because
Now, be careful of this equation. It's a cool equation, but it only works if you're in a state of weightlessness. Okay? Where you're at the top of the loop and you're feeling in a state of weightlessness. If you're not in a state of weightlessness, like for example, if you want to feel like 1/2 your force weight, you can't use this. So it's a lovely equation, but notice I did not put this on your equation sheet because it's such a limited idea. Right? This is not on your equation sheet, and there's a reason why it's not there. You can derive it, be careful of it, but it comes from a much broader idea.
So, what's number 7?
Your answer to number 7 should be something times 10 to the 4th meters.
Okay. But so can you use that on number 7?
AC.
I don't even know what you did.
Yep.
I don't know what you did. You have random things written down, none of which is an equation that I've given you.
V squared over R equals G.
That isn't an equation I gave you.
What?
No. You're at the bottom of the loop. Start with that. Okay. Anything else? Going once, going twice. So, now this video is it's a couple years old. This guy is a reporter for the Atlanta Constitution. And usually when the Blue Angels come into town, they take a sacrificial reporter to take them up and basically see if they can make a furl, or at least pass out. This guy does one of them, as you'll see pretty easily. So basically, he's got a little camera in front of him, and he's going to go along. And so he's going to be subjected to a large amount of centripetal force. Now, what you'll see is that he's going to pass out, and here's the what happened by Albert Einstein. Did you take Al? Okay, so imagine Al is the fighter pilot. Okay, and so the first thing they're going to go up is they're going to go up and they're going to take off like this. Now, your blood has mass. Okay. It has inertia. It wants to travel in a straight line, just like everything else. So what happens is that when you hit the bottom of that curve, or a bank curve like this, your blood wants to travel in a straight line. Unfortunately, that's away from your brain. So what happens is that when you're subjected to these large G-forces, is that the reason people pass out is because basically so much of their blood leaves their body. Now, it isn't pushed away from them. The blood just keeps going in a straight line, but the body is forced away from it. So what you'll see is what happens when you pass out under large G-forces. So,
I love it when you bring anatomy into our lectures, Berg.
it's still on the ground.
Here comes the burners. Oh, yeah. 120. Contact line set up 130. We're smoothly going to start rotating the aircraft. Right. 4 Line it up off the ground. We are airborne. Gear and flaps are coming. There's 220 knots. All right. 230. Wrong one. 260. 280. Are you ready? I am ready. Ready. Hit it.
Now, look how fast the Earth disappears beneath them.
Up we go. Oh, that's beautiful. 3,030 over the tail block. Woo! You're ready for a big pull. We're going to do an angle angle, which is basically pulling right up through the inverted to the vertical to the inverted. Yep. Ready to go? I am ready. All right.
So they're
Flex your leg. Up we go.
now, so the bottom, and now they're going up in a vertical straight up.
If he gets sick, I'm gonna. Oh my god. He looks dead.
That's the inlet.
Pointers.
It's music they tried to play in the background.
Does the pilot have those things around his legs?
Yes, I am. Sorry. No problem.
Sorry.
Wow. I went nowhere there for a while.
Hey, that was like a vertical
All right, that
one.
happens a little bit quite frequently.
They're used to it.
All right, 450 knots. Looking for the obstructions, aircraft looking good. Here we go. Take a deep breath. Flex your legs. Here's the burners.
Now they're horizontal.
He's fighting it so hard. Oh, no.
You see the light.
Oh. Oh, there he is. Come back.
You're back with me.
There's no way that's good for his body.
Can you hear me, Steve? Yes. All right, you're back with me.
He said you never happened. He wants out of
Here
this
we go.
so
Take a
bad.
deep breath. Legs on the flag.
Is he chewing gum?
First year.
And he has some of it. So, anyway. So the reason that they're telling him to flex his legs is up because basically you're constricting those like femoral arteries in your legs, so that by doing that it prevents that blood from going down into your lower extremities. So that's why he was telling you to do that. And but the fighter pilots themselves typically have what they call flight suits, and there's bladders around their legs. And so when the mechanism senses those large G loads, it inflates those bladders, and so it actually squeezes your legs and your torso so that it actually physically prevents that blood from flowing out. Because, you know, if you're flying a $30 million plane, we really don't want you passing out for any number of reasons. That would be bad. Okay, so here's the next big thing. And this is this topic on astronomy, which you'll see is just a natural continuation of centrifugal motion, because that's basically as the Earth is going around the sun, or the moon is going around the Earth, or satellite is orbiting around the Earth. It's basically nothing but centrifugal motion writ large. Okay, that's all it is. So, but to really understand astronomy, you need to understand the history of how we got here. And when you look at kind of the missteps that science has made through the years, astronomy ranks right up there. Okay, we've doinked up a lot of things. We really have. So, but if you go back in time, you go back even to ancient Greece, and Aristotle and Plato and Socrates and all of the big hitters. So, and even from a biblical perspective, everybody thought that we were the center of the universe, and it makes sense. You go out in the morning, you see the sun come up, you see it go, you see it set. You see the moon rise. It follows the exact same path across the sky that the sun does. The moon doesn't look any further away than the sun. Seriously. I mean, if you look at it, don't stare at the sun, that would be bad. But if you look at the path of them, and everybody readily accepts, well, what is the moon? Well, the moon orbits the Earth. Okay, well, that's kind of cool. And then you say, what about the sun? Well, we go around the sun. From a pure observation standpoint, if someone came to you and said, hey, prove it, I'm not buying it. Because I can stand outside in the parking lot and see that sun rise and see that sun set and go, okay, that's reasonable. Hey, I'm stationary. You know, I don't get the feeling that I'm moving at 400 some odd meters per second. I don't get the idea that I'm on a spinning rock that's going around the sun. I get the feeling I'm standing here, I'm not moving. see the sun move. So it would be analogous to me standing over here. I'm going to start here. I'm going to walk over here. I'm going to say, hey, what happened? You all say, well, Burkett, you walk from one side of the room to the other. No, it would be like, I didn't move. You all moved around me. But that's the same idea. So if you look at this idea of the sun moving, or versus the sun being stationary, you can't tell the difference. You don't get the idea that we're on a spinning rock. So, and everybody kind of poo-poos that, like, God, I can't believe they thought that. Well, okay, based upon observations, it's tough to argue. And then you look at the stars, and the stars are also, moving around us. And so, you look at the importance of astronomy. Primarily, that was used for navigation. If you've ever been out on the ocean at night, like away from land, you've got no fixed points. Okay? You can't see land. It is a mass of water. You cannot see anything. So the only game in town are those constellations and those stars. They used it for, religious ceremonies. You look at all the great ancient civilizations, the Greek, the Aztecs, the Mayans, whatever. They all had an astronomy department. Okay? They didn't have a biology department, but they all had an astronomy department. Because they said, okay, hey, this was the realm of gods, and even the American Indians. All the tribes here have rich culture in terms of astronomy. Okay? Moon gods, and every ancient religion had some tie-in with the stars because it was so mysterious. So Aristotle says, hey, we're sun-centered, we're cool, this is it. Bible says God made us in our likeness, we're cool, everything revolves around us. It's the ultimate freshman mentality of like, yes, the universe revolves around me. Okay, it is. It was this freshman year. And we felt good about it. Okay, and it made sense. If I drop Albert Einstein, he falls towards the center of the earth. Everything falls to the center of the earth. And it looks like everything revolves around us. So it was this nice little cohesive idea, and life was good. But there were a couple of problems. And one of the things that they ran into was what's known as retrograde motion. Now, if someone says, oh, you're looking retro today in your fashion, what does that mean? Old, right? You're old school. You've gone back in time. Okay? So what they would notice, especially with Mars, is it would undergo what they call retrograde motion. So let's say that you've got like the constellation Orion. You have the belt of Orion, and then the shoulder, and then the sword, and all this good stuff. And so what they would do over a period of time is that they would see Mars over maybe like 4 or 5 months, each night drift a little bit to the left of the constellation Orion. Now you have to keep in mind, if you've never really spent some time outside looking at the stars, if you translate the word planets from the ancient Greece, it means wanderers. So the constellations were always fixed. So like right now, if I go with this analogy of the constellations, so right now if I look at Kendra, okay? Kendra is in the constellation roller coaster, okay? That's where she's at. Now, if I see Kendra move slowly to the left of the roller coaster, because the roller coaster is a fixed point in the room. So I would see Kendra moving to the left of the constellation roller coaster. Okay, I get an idea of which direction she's drifting. Now, then all of a sudden, Kendra, for whatever reason, starts to go back. She starts to move back to the right a little bit. And she does this for about a certain period of time. And then she stops. And then she keeps going in the normal path, like I would expect her to go. So this period of time is what's known as retrograde motion. All the planets did it. It wasn't just Mars. They all did it. So they're going, hum. What could be causing this? So you have to keep in mind that, and this didn't happen in one night. This retrograde motion takes like 3 or 4 months for this to occur. It isn't like, oh, I'm looking at Mars and it stops and then it goes back and then it goes forward again. Okay? Does not happen in one night. This is over a very long period of time. So here was the perspective they said. They said, okay, here's the Earth, here's Mars, and again, we're seeing Mars, okay, relative to these constellations that are in the background. So they said, okay, well, we've got to somehow explain how this happens. So what they developed is what they called these little suborbitals that would come along and go around like this, and then they would continue on their their way. Okay, so they're going along, it hits this point, okay, called an epicycle, and then it goes back, boom, like this. Now, we all look at this and go, okay, that's just weird, because you would have to have something going along, pull Mars out of its orbit, have an orbit around that point, and then continue on its way. Now, you have to keep in mind the timing. This is 1500s. This is well before Newton had published his work, The Principia. All they were doing is making observations. So these epicycles, as jacked up as they were, worked phenomenally well. I mean, they could predict exactly when they collected enough data. They knew exactly when Mars would do it, when Saturn, Jupiter, all the planets would do it. And it worked. So they said, okay, it's here, it goes around, boom. So it would be like Kendra walking along, and then Kendra's going to go like this, start walking backwards, boom, okay? And then she's going to go about her normal way. And it would work. So that's how I could explain Kendra changing direction. And it worked. So there's a couple big players in this story. First one is Nicholas Copernicus, who was a Polish monk. So Copernicus was the first one to really embrace this idea of what we call a heliocentric solar system, okay, versus geocentric with its Earth center. So Copernicus comes along and says, I'm not buying it. I got a working model. This is what I think is going to happen. However, Copernicus was a monk. He worked for the church. He really didn't want to get fired. So, and there was this deep-seated belief that he actually would not allow his works to be published until after his death. So he basically went to his brother monks and said, here's this piece of work that explains the sun-centered solar system. I don't want to deal with it. After I'm dead, then you can publish it. So, okay, all right. So Copernicus was the first one to really come up with this idea that says, hey, things don't work. So that was the first one. Second one was a guy by the name, here's the most interesting guy, a guy by the name of Tycho Brahe, T-Y-C-H-O-B-R-A-H-E, okay, Tycho Brahe. So, a little background on Tycho. Tycho was a Danish nobleman, which basically means that he didn't have a job, okay, he didn't have to work, he had a lot of money, okay. So, but he had a keen interest in astronomy. So he took an island in the North Sea and basically built his own observatory. Now, this was before the invention of the telescope. Okay? Galileo hadn't come along and perfected the use of the telescope. But what he did is he built this huge complex device to track and measure the position of all the planets. And he did this for like 25, 30 years. He had years and years and years of data, but he really didn't know what to do with it. Now, if you ever look up a picture of Tycho, usually you'll see him with a gold nose, okay? Legend has it that Tycho got into an argument with another Danish nobleman about how to solve a mathematical formula. They took their math really serious. And tempers flared, swords were drawn, and he got his nose cut off in the duel, okay, over how to solve a mathematical formula. So he didn't want to be seen, you know, just without a nose. He had a lot of money, so he was like the first kind of Danish bling guy, and he had a gold nose made. Okay? No, true story. Now, don't ask me, I don't know if he could smell, and I don't know how he held it on. Okay? I don't know. But if you ever see him, he's got this huge handlebar mustache and a gold nose. Eric?
Did he win the duel though?
I don't know.
This is for real though? Like, you actually
Yeah.
recorded those?
Yes, he did. Yeah.
What's his name? Tycho Brahe?
Yeah. T-Y-C-H.
Look that up.
There. Okay? Some pictures have it with it, some don't. So, when you look at this, so Tycho goes, hey, I've got all of this data. So this is happening late 1500s. So the next big hitter on the story is a guy by the name of Johannes Kepler. Now, Kepler had issues. He did. He was known as the wandering mathematician. So he was of German descent, but he's kind of traveled all over Europe. And again, this is in the 1500s, okay? So Kepler had firmly embraced, did you find it?
Yeah, that's weird.
Yeah.
His mustache is super long.
Yeah,
I told you.
yeah, his
Okay.
mustache is-
So they didn't have anything else to do. So you have to, if there's anyone in history, you have to understand their mindset. It's Johannes Kepler. So Kepler believed, number one, in a very, very firm belief in the Copernican solar system, that it was a sun-centered solar system. He also believed that there should be a very easy mathematical way to describe the motions of the planets. Just like you could derive a formula to describe the working mechanisms of a clock, he kind of viewed the solar system as a clock. And so in his mind, and this is exactly his mindset, he thought he was placed on Earth by God to discover the workings of the universe, to find a mathematical way to describe the motions of the planets. Okay, this is important. So if anybody seen the movie The Blues Brothers? Okay, for those of you that have, right? Best line in the movie: "We're on a mission from God." Okay, that's how Kepler viewed this thing. He was on a mission from God. So one of his things he says is, just like a bird is born to sing, I was born to do mathematics, which is kind of weird if you think about it. Okay? Anyway, that was his mindset. So he comes along and he says, okay, he needs data. He needs years and years and years and years of data about where the planets are. And he hears of Tycho Brahe. He says, wow, this guy has what I need. So he goes to Tycho and he says, yo, Tycho. So.
Your calculations are dope.
Yeah. No, actually they're observations. Okay.
Yeah. And then he did.
And Tycho actually came up with his own solar system. It was called the Tychonic solar system, which was kind of a blend of Earth-centered and sun-centered. Okay, so it was cool. He had his own solar system. But he could do it every one. So Kepler goes to Tycho and he says, look, I'm on a mission from God. I need your data. So Tycho says, fine, upon my death, you can have the data. Now,
murders him.
Spoiler.
So everything's cool. Kepler thinks he's set. He's just waiting for the old man to die. And he does. So, but his family, Tycho's family, says, it's kind of a family heirloom. It's all of this data. We really want to keep. We're not going to give it to you. Kepler at this point has a moral quandary. He says, I'm on a mission from God. Stealing is wrong, but I really, really, really need the data. So one version of the story, which I like, is that he actually storms the castle, steals the data, and escapes back to Germany. So the first 3 laws of planetary motion were developed with stolen data from a dead guy with a gold nose. It's kind of weird if you think about it.
Science is cool.
It is. If you look at the history of science, there's any number of people like that. Like Antoine Lavoisier, who discovered the law of definite proportions, was on the wrong side of the French Revolution and was beheaded with a guillotine. Okay.
What's the other side of the story that you don't like?
Well, the other one is that the family just gave it to him, and that's just kind of
I don't like that.
Yeah, it's like, okay, who cares? Point is, he ended up with the data.
Okay.
Okay, just like there's some pictures of Tycho, he doesn't have the gold nose, boring. I like the ones.
Let's just put the gold nose on it.
Yeah, there you go. Okay, so at this point, Kepler has the data. Now, you have to understand the complexity of what he had and what he had to work with. So, when he was looking at this data, number one, he wasn't even sure that it was a sun-centered solar system. Okay, that was the first issue. He kind of felt that way, but it really wasn't completely good about his model. So then, his observations were made on an Earth that's spinning. Okay, it isn't like he's at a fixed point. And then it turns out that he's making this observation about Mars, and Mars, it turns out, travels in an ellipse, and it's always changing speed. It's either speeding up or slowing down. So Kepler is on a rotating platform trying to figure out what's happening with Mars, that Mars is always speeding up or slowing down, and he's got to try and figure this out. Now, he doesn't have Google, he doesn't have a calculator, he doesn't even have Oreos. So he has, true, he has a whole bunch of things stacked against him. Any of the three would be okay, but all three of them are missing.
He does have observations, though.
But he does have observations that he's done. Okay, so there's a couple of things that you have to keep in mind about what he was able to do. So about once every 2 years, the Earth and Mars line up in what we call opposition. Okay? So here's the Earth, here's Mars. So this is like seeing a full moon. So when the Earth and Mars are completely lined up, and this is looking down on top of the solar system. So you would see Mars rise at sunset just like a full moon, and then you would see Mars set at sunrise. And you would be able to see the entire face of Mars. Now, let's talk about the interior planets. Okay? Mercury and Venus. Is it ever possible to see a full Venus or Mercury?
No.
How would it?
I don't know.
Full? What do you mean?
It's like you see a full moon. In other words,
So
is it
not-
ever to see a fully lit side of Mercury or Venus?
No.
Why not?
Because the sun is a shadow of the side that you see.
Okay? So if, let's say, obviously not to scale, but there's the sun. Okay? So here's the deal. If Mercury is here, okay? First off, when you're here, here's the Earth, here's Mercury, Venus, doesn't make any difference. So if you're standing here, okay, what time of day is it on Earth? Noon, okay? Sun would be directly overhead. So even if you're, so look at this. If Venus is here, number one, you're looking at the dark side of Venus, okay? Because the lit side is towards the sun. Issue number two, you're staring at the sun. Bad combination, okay? You're going to go blind staring at something that you can't see. Now, what if Venus is over here? Then the lit side is facing you, but again, what's the problem?
You're looking at the sun.
Yeah, the sun's in the way. Okay? This big star that we have is in the way. Okay. Now, if Mercury or Venus are over here, then you can see them. Okay? And this is why Mercury and Venus are known as evening and morning planets, because that's the only time you can see them. So if they're here, and as the Earth is coming around like this, going to sunrise, you can see them just before sunrise. If they're over here, you can see them just as the sun sets. So that's why Mercury and Venus especially, is usually, if you see it, it's very, very bright. It'll always be low on the horizon just before sunrise and just after sunset. Okay? It's a very, very bright planet. But you'll never see the full side of it because the sun's in the way, or you're looking at the dark side of it. So he didn't want Mercury or Venus because he had limited data on those, especially Mercury. Mars, though, because it's the closest exterior planet, he had a tremendous amount of data on that. So what he would do is sit here and say, okay, you're here. Now, when you're judging this position, the only thing you can do is judge that position against the background stars, against the constellations, Orion, the North Pole, whatever, North Star, whatever it is. That's how you can judge the position. So Mars might be here. Here's the Earth. You're looking at it. Boom. There you go. Okay. That's where we're going to pick the starting point of Mars to be. But here's the problem. It takes about roughly 2 years for Mars to get back to this point. But here's the problem. The Earth won't be back to this point because it takes the Earth 1 year. It's technically like 1.88 years. So problem being is the Earth in its orbit might be over here. But now, when you're looking at Mars, it's going to look completely different. Because of the fact that even though Mars is back to its same point, it's going to appear in a different constellation because you're viewing it from a different perspective. Okay? So, Kepler had to compensate for all of this and go, wow, you know, his calculations were tremendous. And it took like, I don't remember how many volumes it filled up. So, but again, he was going, I'm on a mission from God. So, he had a spinning Earth trying to keep track of Mars, which was continuously changing speed, but yet, and it took him a long, long time to figure this out. But again, you have to get into his mindset. He's going, this is what I was put on Earth to do. Okay? Now, stop that me.
Sponsored by.
Yeah, you were right.
The test isn't until a week from Monday.
Well,
A week from next Monday?
No, yeah. Chill out.
Yeah.
Yeah, test is tomorrow.
I'm like, oh my god.
No, I'm kidding. Okay, going? All right. So, let's talk about Kepler's 3 laws. Now, these aren't like 3 suggestions. These aren't, well, they're not 3 kind of, okay? These are 3 laws, okay? There are 3 laws. So the first one is the law of ellipses. So for those of you that have studied these in math class, how many foci does any ellipse have?
How many what?
4?
How many foci?
4?
What does that mean?
2?
2.
Oh.
Okay?
Foci?
It's been a long time since like geometry.
Okay?
Or whatever
So
that was.
imagine that these are 2 thumbtacks and you have a string wrapped around it and you draw it like this, where it creates, basically, it ellipses an oval. Now, if you bring these 2 foci together, what do you think happens to the shape? Does it get rounder or flatter?
Rounder.
Rounder. So if you have an ellipse that only has 1 foci, that is a
Circle.
It's a circle. Okay? It's a circle. So when Kepler even came out with his first law, and again, you have to realize the difficulty of what he did. It isn't like he was looking out, and it isn't like there's a path that you can see that Mars rolls around. There's not a track. It isn't like I'm on the inside of like the Indianapolis Speedway, and I can look out and go, oh, that's where the cars are going because there's a track. Well, you've got cars going around a long, long way away, and you can't see the track. And you're trying to figure out the shape of the track, and the only thing you can see is one car, one set of headlights, a long, long, long way away, and you're trying to figure out the shape of the track. Okay? So, he figures out that it's an ellipse, and you wouldn't think that would be a big deal. This was actually a big deal. And this harkens back to the time of Aristotle and even a religious aspect to it. So, the heavens were viewed as the realm of the gods. And they viewed the circle as the perfect geometric shape. This is why wedding rings are round and not like square. So, for any number of reasons. Okay? But wedding rings are round because, oh, our love has no beginning and it has no end. Okay? And all points are...
You gotta love
Okay.
You do. You would marry physics if you could.
No, I wouldn't.
Yeah.
Physics is too weird. I can't deal with the weirdness. If it was Newtonian physics, okay, but you did the
You gotta
quantum
like
stuff.
the weirdness.
There's a quantum side that's just too weird that I can't handle.
Yes.
Okay. Yeah.
You
Anyway.
don't know what's in there yet.
Anyway.
All the G's, baby. All the G's. That shorts.
So, because the heavens were viewed as the realm of God, all the planets and all the stars, they thought traveled in these perfect circles, because that was the perfect geometric shape. So, Kepler comes along and says, bad news, not a circle. Close, it's an ellipse. So everybody was kind of a little bit upset because basically an ellipse is a jacked up circle. So it's like God was trying for a circle, had a bit of an off day, we ended up with an ellipse. Ooh, not so good. Okay? So this was a bit of a stir because everybody said it should travel in perfect circles. Now the good thing about Mars Mars has about a 10-degree eccentricity, which makes it noticeable enough to pick up. If the eccentricity had been much less than that, the first law probably, and the second law probably would have never been discovered. Because the second law is a spin-off from the first law. Okay? So he happened to pick, he got lucky. Mars was eccentric enough that he could make these observations from Tycho's data. So the first law, all you have to remember, law of ellipses. That's all you have to remember. So basically, the sun is one foci, and the second one is some point out in space. So here's one, here's the second one, boom, we go around like this. Now, I completely overdrew this eccentricity. These orbits aren't this eccentric. Pluto's is pretty eccentric. That's one of the most eccentric ones of all the planets. But don't think it's like, wow, it's really like an egg shape. No.
Wouldn't we
okay?
like die if that was the case?
Well,
It'd be
not
like
necessarily
really
die,
hot.
but Earth's orbit is a little bit eccentric, but not very much. Okay. Now, here was the hard thing that he figured out. And that's the second law, which is called the law of equal areas.
Oh yeah. Sports.
Okay. So the second one is the law of equal areas. So what happens here is this. What he did is he said, okay, we're going to look at a certain period of time, maybe 30 days. Okay? So he's going to say, okay, here's Mars on, say, October 1st. And then he's going to look out here and he's going to find Mars on October 30th. Now, if you look at the sequence, he had to have an idea of the radius itself. So then he comes along and he says, okay, this is going to sweep out a certain angle, and then I'm going to find an area. So it's like finding the partial area of a circle. We're going to do these calculations on Monday. So here's what you need to know for now. This is just going to have a certain value of area. Okay? Don't know what it is, don't care, it's a certain number. Then he says, okay, I'm going to come out here when it's at the other end of its orbit. So this might be April 1st to April 30th. Okay? Again, it's the same time period, same 30-day period. Now, out here, you have a much greater radius. Here you've got a really short radius. Here you have a much bigger radius. So what he found, though, is that these two areas that were swept out are the exact same. Okay? So here you've got a short radius, bigger arc length. Out here you have a bigger radius, you have a shorter arc length. So the only way that could happen is if Mars was changing its speed. So when it's closest here, at that smallest radius, so as you make the radius smaller, you increase the velocity. Out here,
This is what you're getting to. Good stuff. I was like, what is he? Where's he going? Now you got it.
okay? Then out here, as you have a bigger radius, you have a smaller velocity. So what that means is that for half of its orbit, it's speeding up. The other half of the orbit is slowing down. Now, this has nothing to do with seasons or anything else like this. This only has to do with how far away you are. So, when you're closer, you're going faster. When you're further away, you're going slower. If you read Kepler, he doesn't really try to explain the mechanism. He's just like a reporter. He goes, hey, I'm not going to try and explain it. I'm just reporting the news. Goes faster when it's closer, slower when it's further away. Because if you think about it, that's a weird mechanism. So here you have this planet that's out in space, speeding up and slowing down. So it would be like, imagine this, you're watching a car go around on a track, speeding up and slowing down, but there's no driver or engine in the car. But yet you see it speeding up and you see it slowing down.
But then you learn the engine.
Just shh. Okay? So it's a little bit weird. It's like, okay, here's this car that's speeding up and slowing down, but there's no mechanism to make it speed up or slow down. But yet clearly it's speeding up and slowing down and I can't even see the racetrack. Okay, this is weird. Okay? But again, Kepler said, I'll muddle through. Okay. So These areas are the same, no matter which areas you pick. You could pick areas in here, you could pick areas in here, doesn't make any difference. So half the orbit is speeding up, half the orbit is slowing down. Got that? Got it. Good. Now the third law. There's various forms of the third law. And this is what I've got. Let me see where's your equation sheet? Is right here underneath the centripetal acceleration. Here's Kepler's third law. It's called law of harmonies. You got TA squared over TB squared equals RA cubed over RD cubed. So what this does is, and the big T's are going to stand for period. Okay, this is the period for one rotation. So this is period, and then the R's are going to be what? Radius. So this is a cool deal. But so basically, the third law is what's known as the law of harmony. And so, Kepler thought this was like a clockwork mechanism. So this is a cool deal, and it works, but you have to be very careful. First off, this only works for objects that orbit the same center. Like, you could compare the 4 Galilean moons of Jupiter, Ganymede, Callisto, Europa, Ida. So you could use this with the 4 moons of Jupiter, because they all orbit Jupiter. But you can't use this to compare a moon of Jupiter with our moon, because our moon orbits us, those moons orbit Jupiter. So you can only use them if they orbit the same center.
Wait. So if you have 2 moons.
So like if the Earth had 2 moons, I could use this with the 2 moons.
What are you trying to find? Just the area?
No. But we'll get there. Okay? We'll get there. So, the other thing that you have to keep in mind about Kepler is this. He did not have Google. No one knew the actual distances from the sun to the Earth. Okay? They didn't know the actual distances. Now think about this. You're Kepler. You don't have Google, you don't have a calculator, and you don't have Oreos. And you're trying to find this relationship. What is your favorite number? 1. You are going to use a numeric value of 1 every chance that you get. Because using like 3.52 times 10 to the 13th would just be weird if you're trying to square and cube and do all this other stuff. And they didn't even know what they were anyway. It isn't like he could ask his phone, excuse me, Siri, what's the distance from Earth to the moon? Okay, or from Earth to the sun? Okay? People would burn him at the stake because they thought he was a witch anyway. So it didn't even have that available. So he says, okay, I like the number 1. So what he did, he said, okay, here's the sun, here's the Earth, and he let this distance from the sun to the Earth be 1 AU. Anybody know what AU stands for? Astronomical unit. Okay? So Kepler said, I don't know the distance, I get to pick it, I'm going to let it be what? He could let it be 4. He could have let it be 13.2. Doesn't make any difference, but he was smart. He goes, it's bad enough I had to steal the data. I'm going to make this easy. Okay, so he's going to let this be 1. So he knew Mars was further out. Okay? So he knew that the orbital radius of Mars had to be bigger than 1 because it was further out. He knew Mercury and Venus had to have an orbital radius of less than 1. Now, you have to keep in mind, this is not a distance, okay, like a known distance. This is all set up as a ratio. So, even though this is how this is on your equation sheet, the simplified way of using this is if you cross multiply. So, if you write this as TA squared, RB cubed is going to equal TB squared times RA cubed. Now, here's where Kepler got really, really clever. He says, wow, okay, I got all this happening. So let's say that we want to compare Mercury and the Earth, for example. So we've got the period of the Earth, we've got the period of Mercury, we've got the radius of the Earth, we have the radius of Mercury. Now, if you're clever, what are you going to let the period of the Earth be? 365.25 days or 1 year? Let's go with 1 year, okay? Because that's much easier to work with. What are you going to let the radius of the Earth be? 1
AU.
astronomical unit. Okay? Now, here's where the magic happens. So I'm going to rewrite this as a period of the Earth times the radius of Mercury cubed, and then the period of Mercury squared and the radius of Earth cubed. Now, here's where the magic happens. As complicated as this looks, if you let the period of the Earth be 1 year, 1 squared is 1. So this, mathematically, just becomes 1. Over here, you're going to let the radius of the Earth be 1 astronomical unit. That effectively drops out. So if, and this only works, this is a huge if you let one of the sets of period and radius have a value of 1, it drops out of the equation. So basically what you end up with is saying the radius of Mercury cubed is equal to the period of Mercury squared. Now, if God really wanted to make it easy on Kepler, what would have been the easiest ratio to have? Yeah, 1 to 2 or 1 to 1 ratio, something like that. Like if Mars is twice as far, the orbital period would be twice as much. Okay, where it would be like a straight linear proportion. It wasn't bad. There were some squares and cubes. Okay, if you've ever even tried to take the square root by hand, okay, like if I say, hey, what's the square root of 123? And you go, I don't know. Try to do that by hand, you kind of guess and check and all this good stuff. So imagine kind of trying to do that with cubes, okay? It really sucks. So I just point this out, so if you look at everything that Kepler had going against him, squares, cubes, stolen data, got to pour over that, feeling guilty because he's on a mission for God. It's like, do I take a vacation and go to the Bahamas? Oh, no, I got to stay and work on a mission from God. So here's the beauty of this. So basically, if you let one of the values be 1, then it becomes very simple to do. So let's say, for example, that I'm going to let the radius of Mercury, just to make up a number, let's say that's 0.70 AUs. Okay? So if this is the radius of Mercury, what's going to be the period of Mercury? What are you going to have to do? So you got the radius of Mercury, 0.7. I got that. So I'm going to take 0.7, and I'm going to cube it, and then that has to equal the period squared. So then what I'm going to do? How am I going to get this by itself?
Square root.
Yeah. I'm going to take the square root. So somebody take 0.7 cubed, and then take the square root of that. What'd you get?
0.5856.
So 0.586.
6.
Now, here's what this is. This is technically 0.586 Earth years, which should make sense. Okay, Mercury is inside of Earth, should take less time. So if you want to get like the number of days, out of curiosity, take that, multiply that by 0.586. Take 365 times 0.586.
213.77.
Yeah, so based upon this, Mercury's orbit should be about 213, which it isn't. It's actually about around 90, but I'm just showing you this as an example. So when you have problems like this, okay, when you have problems like this, if you can let two of the values, if you can let a period and a radius have a value of 1, then it's just this squared and that cubed. If you can't, then you have to work the full Monty, and you have to work with all 4 variables. But you'll always know at least 3, and you can solve for the 4th one. Got it? Good? Okay. Stop. Okay, so let me kind of take you through what you have. So you've got, let me start you with this. You've got this polar graph, and then you have this set of data. So one of the things that you need to do is plot We good?
Copy.
Okay.
Okay, well done.
So here's what you're going to do. You're going to plot this data on this polar graph. So let me give you a hint so that you don't go blind staring at concentric circles. Most of this data, these radii are between 0.3 and 0.4. So what I would do is I would take like a highlighter or even like a colored pencil or something, and I would put in different colors the 0.3 line and the 0.4 line. Okay? It's going to make it easier to see. That way you're not going crazy staring at these lines. So what you're going to do is you're going to go to October 1st. You've got a radius of 0.319 AU and 114 degrees. So you're going to go up here to 114 degrees. You're going to find that radius of 0.319, make a dot. So this is just like a circular graph. You're going to do that all the way around for all of these points. Draw a line that connects them. About every third point, write the date beside it. You don't have to put the date on every point, because on Monday, then we're going to start looking at where Mercury is at specific times. And if you already have the dates on here, then it's just going to save you some hassle trying to work backwards where it is. You don't have to put every date down. You have to plot every point, but you don't have to write down every date. Okay? So that's one thing. Then you've got, let me see the actual sheet. So, no, there's not a backside. All of these deal with Kepler's 3 laws. If you go through this, and so for example, if you look at number 5, you got Jupiter is 5.4 times farther from the Earth than the Sun is, determines Jupiter orbital period in Earth years. And I tell you, let the radius of the Earth be 1 astronomical unit, let the period of the Earth be 1 year. That way, you can drop those out, and basically it's going to simplify down to the period of Jupiter squared is going to equal the radius of Jupiter cubed. Okay? Now, keep in mind what units that you're going to end up in. You're either going to end up in astronomical units or you're going to end up in years. Now, here's the only time you will ever hear me say this in this class. When you have this relationship, this is a ratio. The radius can be in any units that you want it to be. It can be in astronomical units, kilometers, inches, picometers. I don't care. It's a ratio. The period can be in any units that you want it to be. Hours, days, seconds, milliseconds, whatever. Okay? As long as they're the same. Right? It's the only time you will ever hear me say this. The units just have to be the same because it's a ratio. So keep that in mind. Okay, I'm done. You're on your own.